Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series with academics of the IT Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our webinar today with Professor Mehdi Bennis from the University of Oulu, Finland. We count on your support to make this webinar an interesting experience. So please submit your questions via the Q&A channel. We will address them to our speaker during the Q&A session. After the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live lessons. So please stay online. Professor Bennis agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm very pleased to introduce now Professor Ian Akyildiz, Editor-in-Chief of the ITU Journal and founder and president of Truva from the United States. Professor Akyildiz is Ken Byers Chair Professor in Telecommunications Emeritus at Georgia Institute of Technology. Professor Akyildiz has established many research centers worldwide, including in South Africa, in Spain, in Saudi Arabia, and in Finland. He's Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international rankings. Ian is visiting distinguished professor in several universities around the world. His current research interests are in 6G, 7G wireless communication systems, hologram communication, terahertz, molecular communication, Internet of Bio-Nanothings, intelligent surfaces, nanonetworks, Internet of Things in challenged environments, and many other subjects. So I'm very pleased to give the floor to Professor Akyildiz for his opening remarks, to introduce our speaker, and to moderate the Q&A session. Ian, the floor is yours.
Thank you, Alessia. Greetings from Ljubljana in Slovenia to all around the world. I welcome you all to our another ITU Journal of Future and Evolving Technologies webinar series. We have another very promising speaker today, Professor Mehdi Bennis from University of Oulu, Finland. Before I present Mehdi, I would like to briefly talk about our journal. The objective of our journal is to bring the academic and industrial worlds together in order to establish a strong bridge between academia and industry. The idea for our journal was initiated back in December 2019, and our first issue was published in December 2020. It is an open access journal, no fees for readers, no fees for authors. The papers go through a rigorous review process, and we try to cover all forefront and timely research activities in the academic and industrial world. The journal is a product of a big team effort, and I would like to acknowledge them here. Sijo Ono-san, Bilal Jamusi, Alessia Magliarditi, and Erika Campilongo, and many others for their work, efforts, continuous support, and dedication for the success of our journal. I encourage you all to submit your papers, and also if you have ideas for special issues on popular topics, please do not hesitate to contact us. Today, I have the great pleasure to present you our speaker, Professor Mehdi Bennis. First of all, on behalf of our entire journal team, I personally thank Mehdi for accepting our invitation and giving this webinar today. Mehdi is a professor at the Center for Wireless Communications at the University of Oulu in Finland. He is an IEEE fellow and head of the Intelligent Connectivity and Network Systems Group. He has published more than 400 research papers in international conferences, journals, and book chapters. He has been recipient of several prestigious awards, including 2015 Fred W. Ellerslie Prize from the IEEE Communication Society, 2016 Best Tutorial Prize from the IEEE Communication Society again, 2017 EuroSIP Best Paper Award for the Journal of Wireless Communications and Networks, the Old University of Oulu Award for Research, the 2019 IEEE ComSec Radio Communications Committee Early Achievement Award, and 2023 Clarivate Highly Cited Researcher by the Web of Science. Based on Google Scholar, Mehdi's H index is 87, and the total number of citations to his papers is 45,000 citations. I follow Mehdi at least 10 years now, and I'm always a fan of his research contributions. He contributed many pioneering papers to our research field. His papers on federated learning became classics in the meantime. His contributions on unmanned air vehicles like drones and also overall 5G and 6G systems are very highly recognized in our research community. In recent years, he focused and obtained many excellent results regarding semantic communications. And today's talk is based on this topic. And Mehdi continues to produce high-class and impactful papers and publishes them in first-rate journals and conferences. And there are many accolades I could mention about Mehdi, but also I like him as a person. He's very pleasant and very intellectual guy, a friend, I can call him. It's always great fun to spend time with him at conferences and in social events. Without further ado, let us listen to Mehdi's exciting talk. Again, thanks, Mehdi.
Thank you very much, Jan, for this great introduction. It's really my pleasure to be with you today. So let me just first start by sharing my screen, and then let me know if you can see. Just a second, I have to hide the...
Yes, we see it, but
perfect.
Make it bigger. You can make it bigger.
Let me just see. Hide the panel. Now it's fine. Can you see it, right?
Alessia, is this fine, or what does she need to do?
No, I think it's okay.
It's perfect. Yeah, we tried before. Yeah. Should be fine. Very good. All right. So the title of my talk will be about semantic communication and protocol learning in the 6G era. I think this is a fundamental topic, in fact, which could be, jump-starting this new generation we call 6G. But also what I'd like to do today is really to give you my take on it, because in fact, it means different things to different people. And then I'll show you, in fact, how this area also build bridges with other disciplines such as robotics, of course, machine learning, and other areas that I think are fascinating, and looking forward to the discussion. So here's my outline. So first I'll start with a motivation, basically, how semantic communication sits within the 6G ecosystem. And then I'll talk about some technical work. So one of them is semantic-native communication. These are early results we obtained a few years ago, basically to show you a little bit the lessons we learned along the way, and maybe some mistakes that I can, of course, share with you as well, and then how we should take the topic further. Then I'll jump into a learning communication protocol, which I think is very related and very important. How do you learn protocols using machine learning for various verticals? This could be your robots, it could be your, your drones, human-machine interaction, and then a bunch of other works which are actually ongoing and finally unconcluded. All right. So let's start with the state of affairs of 6G. I always like to start kind of playing devil's advocate of 6G. So as we all know, right, so 6G promised to bridge digital, physical, and biological worlds, right? But in fact, I mean, the growing consensus today, in fact, if you look at all the white papers we have, the current vision, in fact, is really nothing but 5G plus, right? So what do I mean by that? In fact, if you look at the 6G vision today, it's really about taking, for example, deploying more base stations, right? More bits per second per hertz, the better. But we know this is a not sustainable solution, right? Some people take, for example, 5G requirement, let's say in terms of packet error rate, right? And maybe multiplying them by, if it's 5 nines in 5G, let's do 20 nines in 6G, right? This is also not sustainable. Actually, if you talk to robotics people like Kuka, they would tell you actually that there's no problem to lose, let's say, 3 to 5 consecutive packets. There is no need to over-provision the over-the-air link connectivity, right? So this is something we should keep in mind, right? Of course, taking 5G and adding AI and calling it a new generation is also a little bit myopic in the sense that today AI is really brittle, it's energy hungry, it's just doing curve fitting. And I'll come back to this a bit later. So you can see, I mean, this is some of the KPIs. So peak data rate, 5G. I mean, if it was 200 gigabit per second, of course, now it's 1 terabit per second. And you just take your favorite KPI and just see what happens when you go from 5 to 6G. This is really an engineering, I think, insight. There may be reasons why we do that, perhaps because they are based on Shannon's level A or technical level definition. I'll come back to it later. But also what I realized since we started working on this 6G, in fact, there are some words we use without understanding them. So of course, one of them is semantic communication, but also another one, which I think is fascinating and relates to semantic communication, is resiliency. In fact, what I have done for you maybe 2 years ago, I kind of ran this survey asking people, actually, these are the NSF Rings program people. So R is resiliency, NSF program, asking them basically what's resiliency for you. So as you can see here, it's in fact, for some, resiliency was reliability, 21%, right? For others was dependability. This term was coined, I think, by FedVice. For some, it's robustness. 39% said it's robustness. So I think this is a good sign to show us, in fact, that we have to do more work to understand a bit what resiliency means, and I'll come back to it a bit at the end of my talk. In short, at least my take on 6G today is really nothing but 5G plus. Okay. So now, of course, this is where kind of the semantic communication comes to challenge a bit the statu quo. Instead of the bigger, the better, can we flip a bit the paradigm upside down by asking 2 questions? There could be more, but these are 2. So first one, can we transmit less by instead reasoning, thinking, and planning to basically relax some of these requirements? This is exactly what human brains do, right? So I mean, the whole talk today will be really inspired by brains, by the way, right? Now, 6G promised to be about machine-to-machine collaboration or human-machine interaction. So the question here is really, again, can we learn from humans' modes of cognition, which is in fact called or referred to as System 1, System 2. I'm not sure if you're familiar with this. The System 1, System 2 was coined by Daniel Kahneman, who is a famous psychologist, actually passed away last month, essentially telling us that there are 2 modes of cognition. Again, I mean, this is, of course, neuroscience now here. So System 1 is, in fact, the one that's your reflexive mode, right? Which is fast. It's basically just pattern matching. Maybe you've seen some data before and you know exactly how to act in the world, or think of it as an Excel sheet, right? And it's just interpolating, right? So for us in machine learning perspective, this rings a bell because that's exactly what we have been using for many decades, right? But it turns out there's another system called System 2, which is slower because in fact you have to plan, you have to reason, you have to do counterfactual reasoning. What would have happened if I have chosen a different course of action? And this allows you to, of course, generalize outside of distribution if you're a machine learning person, also to handle exceptions, right? So in fact, the thesis of semantic communication is this is exactly the mode we are missing today. We're missing planning and reasoning in networks, in communication. And that's a bit what semantic communication is really coming here to fill, right, as a gap. So, and just as a spoiler, perhaps, so all the works today in semantic communication, including some of my group, are really nothing but just a System 1 type approach. This includes machine learning for X, so physical layer, layer 2 and above, right? deep joint source channel coding. It's really just system one approach. And I'll show you what I mean by that. So I believe, of course, now to push the frontier further, we need to, of course, look at what kind of technical revolution we have. So the first one, obviously, is what's referred to as post-Shannon era. Some people don't like to use the word post-Shannon, but I'll tell you what I mean by that. In fact, we have to go a bit backward to the 1948 paper, the landmark paper of Shannon, right? Which basically give us three definitions of communication, right? We have the level A here, right? That's saying basically to accurately transmit symbols from point A to point B, right? I mean, you have X here, this is your source, right? Then you can maybe do some source channel encoding. You maybe want to add redundancy in the channel. You have noise. And then the whole point is really to just do X equals X hat, right? So basically there, back in the days at least Second World War, is so Shannon removed all the structure, all the meaning, all the context, basically just reproduce the same thing sent from the source at the destination, right? And of course, I mean, we all know this. I mean, what's information in the case of Shannon? This is just a statistical description of information. It's basically entropy of X, okay? Just to make this very clear here. And of course, again, as I said, it's really just how do you best encode the information at the transmitter and how do you best reconstruct it at the receiver. It turns out that actually Shannon himself wrote a paper in 1948 called The Bandwagon, telling us that this level A should not be used when you want to talk about biological systems communicating. So there is this level B, level C here, which says that level B is really how the transmitter is actually conveying the meaning to the receiver, right? And then level C, which basically says that how does the receiver now act upon the meaning received from the source, right? I mean, it makes sense, of course. Again, this is really brain inspired, so everything makes sense. And of course, now we talk about adding meaning, adding structure, and adding memory. So a lot of semantic communication talk, you will see these things. But my take on it, in fact, I want to go a little bit further by now asking, what's level B? What's level C? So in my mind, what's level B is really about learning concepts, abstractions, equivalence classes from data. This is number one, because we always have to learn abstraction. We don't deal with pixels in an image. We really try to understand basically that image is composed of objects and relationship, right? That's abstraction I need to learn. And then, of course, now we have agents. So now you have agents interacting in an environment. This could be, again, robots, right? So sensing is there, obviously, but also the agents have to reason about other agents' intents, goals, and beliefs. We just don't come and send random information to the receiver. I need to basically have some sort of a model of the other agent to send him or her or it the most important information, right? So you can see here, this is really nice because it gives us a good grounding in terms of sensing, planning, actuation, reasoning, and so on and so forth, which basically already tells us now we have to deal with agency, dynamical control loop systems. That's the right jargon to start to work on semantic communication. Not the way we have been doing so far, meaning just supervised learning with labeled data and we train a model and send it from point A to point B. That's not what humans do, okay? And also, very interestingly, now to contrast information from Shannon world to this world, now we talk about information as a topological space. Now we have to think of information as a shape, and I will show you examples of that. So think of the intrinsic geometry or topology of the data. That's information, right? So sometimes information is really what we call a topologically invariant. What doesn't change is information for us, and I will show you again what I mean by that, okay? And of course, as you already know, everything is called semantic com, which is, of course, confusing today. So for some people, it's really semantic empowered, rate distortion, compression, deep joint source channel coding. I think that Future Way had a concept called qualitative communication. Of course, goal task-oriented communication, emergent communication. As you can see, I mean, it's a lot of things, right? And maybe there's a way to unify all this jargon and this syntax, right? Likewise, what is semantic information? You may ask people, you have totally different answers, right? So for some, it's really about the importance of data. The community working in age of information, for example, for them, semantic information is really related to the freshness of the information received by the receiver, okay? You also have value of information and other variants. if you talk to machine learning folks, perhaps for them, it really is just the extrinsic attributes of an object. So if you have an image, it's a cat and a dog, okay? That's semantic information. Also, if you use machine learning, of course, now we talk about, of course, large language models, but if you want to look inside what kind of representations those LLMs encode, that's called also semantic information, right? But what's interesting, I think, to note is that information is not a property of let's say, Shannon. Shannon information is one, obviously, but now if you go and look at, for example, there is this very famous Carnap-Arbar-Hillel paper in '52, which was the only serious paper that appeared after Shannon paper, which is actually looking at a different notion of information. So Shannon information, I told you, which is like entropy of X, right? A set of random variables, which is a number, a scalar. Here you can see this is a set valued notion of information. Point being here is that we try to go from a scalar, which doesn't mean much, towards adding more structure. So what comes after a scalar? A set. So, right, that's what he has here. And of course, you need to also define what kind of language are you dealing with. So in this case, he already worked on a different type of language. So this is a propositional Boolean language, logic language, right? So think of it, let's say, of an image, and you want to, take every pixel of the image and maybe, encode the fact that, the RGB values of that image, and then write down that 1 million long formula describing the image, okay? So now, of course, what semantic information there will be really the set descriptors that allow you to tell this is a cat or a dog. So it's kind of toy example, but just to convey a bit the message. It could be one of the reasons why we don't use this kind of information today, right? It could be a reason because, of course, of the computational aspects. But I believe we have to bring back logic. This is kind of a message today that I'd like to argue for, right? And of course, I mean, if you talk to logicians, which are people we should interact with more, there is a notion of truth conditional semantics, right? There's this notion we are currently working in the group now, which is this idea of Kripke semantic, which is the kind of multi-agent epistemic logic, right? Think of agents now navigating the world. And now, of course, they cannot rely on statistical models. These guys, these robots have to now try to basically label whether a model is, for example, true and false, right? So, for example, if an extension would be the formula, the logical formula that you try to prove, meaning this property is true, this property is false, right? Then the intention, which would be the semantic information of that formula, is really what we call now semantic information, okay? So we have to keep this in mind, right? Something I will show you today, also there's information as topological invariance and shape. We always have this nice example, which you say that a donut and a coffee cup are the same. This sameness, this equivalence is related to the number of holes, right, that a coffee cup and a donut have. So this is a very, very important to keep in mind. And of course, now, if you really want to use the right mathematical terms, what we really need to talk about is information, and don't stop here, but information structures and categories. This is exactly the right way, because in fact, I need the collection, I need a universe or a collection of objects, which could be a model, right? And this is exactly where I can analyze and describe information, okay? Anyways, now the second technological revolution, of course, is AI. And I think now it's quite clear, in fact, to people that, we've been obsessed a bit with, with test accuracy and just maximizing the accuracy of a model, disregarding the sustainability. So of course, now we talk about it. Perhaps we don't even have a definition of it, but we know we need to train green models, of course, right? Energy bill is, of course, important, right? Not just optimize test accuracy, but what about trading off with energy and robustness? I told you before, the main, today, system one machine learning is nothing new, right? It's just basically, whether big data or small data, the problem is that it's really brittle. It doesn't generalize, right? Even federated learning, which my group was one of the first actually to jump on, Jan was mentioning that, we thought back in the days that that's it, this is the key revolution, right? But in fact, as now we realize, it's nothing but a function approximator at best. Okay, that's it. There's nothing else. Okay, of course we can write papers, which is fine, but we know that's not how humans brain do. The system 2 part is missing, which means the one that's lacking, of course, reasoning, extrapolation, imagination. So we have this ability to think before speaking, right? So our grandma says, you know, turn your tongue 7 times before you spit something. This planning module is really what we need to bring into the fore. And actually, this is exactly where the AI gurus, Yann LeCun, Bengio, are currently working on. And I'll show you how we kind of build a bridge between them, okay? Then, of course, abstraction is a big missing piece in AI, concept learning. I mean, things that I think that are kind of obvious here, right? And also sometimes what we really want to do is to basically have this algebraic compositionality. If I have 2 concepts, I want to compose them together and maybe do hypothesis testing, right? I have 2 agents, I want to compose them to maybe emerge a bigger agent, right? So this algebra is, I think, something fundamentally missing today, okay? So we came up actually with this kind of 6 desiderata, which we think kind of are minimally needed to have a richer model. So of course, one of them is the model has to be a function of the data. I think it's kind of clear. It has to be minimal, right? Yet sufficient to solve a task. That's what people call maybe goal-oriented, right? I mean, there's nothing new here. So all the variation autoencoder families or GANs are really just satisfying 1 and 2. What's actually missing to some extent is the invariance. So invariance, in fact, is a kind of a mathematical construct which we actually use without realizing it. So CNN, convolutional neural networks, have translation invariant, meaning you rotate an image, it's still the same cat or same dog, right? But now what I mean now, can I do that? Can I look? Can I learn invariance, for example, in the environment, which could be a robot navigating the world? What is a symmetry? It has to learn the symmetry of the world before it starts to maybe plan its path, right? So invariance is very important to rotation, translation, symmetries, right? Disentanglement, because you need this ability to break down your object in terms of, maybe atomic elements to recombine. So, right, this is the idea. You need to break down in terms of pieces to piece them again and maybe do some, compositional abstraction, compositional thinking, right? Causality, obviously, because, I mean, we know we need that. It's a hard topic, obviously, just to go beyond statistical models. And everything has to be emergent, meaning that even information has to emerge via interaction between an agent and an environment. And multiple robots, they don't come pre-hard-coded with information. That information has really to emerge. So in other words, coupling between agent and environment is the way to basically transfer information. For people working in dynamic systems, this is boring speech, but I think we need to bring this to our folks because they completely ignore these things. So as I told you, there are some mistakes we learned along the way. So hopefully that will be also interesting for you. And of course, now a new objective, instead of just training one model, which is useless for as soon as you change the task, now what we need to learn is actually a collection of models, right? This category that lists this library, if you wish, of models. And then I can go from one model to another, maybe by combining them, composing them, and so on and so forth, right? For solving a task. So X could be inference, training, planning, reasoning. And something extremely important, which we ignored a few years ago, we should avoid using supervised learning for many reasons. 1, the label data is not always available. 2, maybe sparse. 3, maybe completely wrong, erroneous. And again, humans do acquire their own labeling data via self-supervision, via sensory motor signals, meaning you're moving in the world and acquiring the most informative information before training your model. Okay, that's the right way to see things. So what I have done actually is to kind of deconstruct and unify these different philosophies or ways to look at the topic. So this is one way, and I call them System 1 versus System 2. Semantic communication, kind of a nice way to also bridge with AI, because as I told you, that's the main way now how to differentiate between, let's say, easy AI and difficult AI, right? And also for communication, right? So today we have System 1 semantic communication already. So what is it actually? So System 1 semantic communication, you can look at it from a different perspective. maybe because it doesn't have any agency, so it's purely supervised learning. And also maybe because it operates in data space, right? And I'll show you what I mean by that. So for example, you can have an URLLC EMBB traffic. So you have a user looking at a scene, and maybe you will tell me that, okay, semantic com maybe now is to just render the URLLC resources. Okay, we mute the EMBB. Some people claim that, right? I mean, I think it's kind of very naive way, right? As I told you, the AOI crowd community, for them, semantic com is really just the freshness of a packet. Well, if that's the case, then we have been working on this topic many years ago. We just didn't use the word semantic, right? A very interesting toy example proposed by Huawei, Globecom 2019 or 18, before OpenAI was born, okay? So they had this idea, this is an image of a dog. So they say, don't send the image, don't compress the image, transform it from image to text, right? That's the DALL-E and clip techniques now proposed by OpenAI. And then you send, this is a dog over the wireless, and then the receiver can generate the same dog or totally different dog. It's kind of straightforward idea. And maybe 2018, 2019, this was wow. Of course, today, I mean, there's nothing new here. But some people will claim this is semantic communication, okay? We also, in my group, worked on LLMs, of course. I mean, we had to check the hype a bit, right? So we had this idea, this is a base station with the pre-trained model, Llama here. And then it's remotely controlling two agents navigating the world. So here you could argue that this is a semantic com because now these are kind of robots, if you want. They have the image camera, and then they don't send the image camera. They translate the image camera to a prompt and send the prompt to the base station. And then the base station just control remotely these users. I mean, it's kind of naive. I don't claim this is system 2, okay, or system or semantical, okay. In short, really here, semantics is really the fresher the better. It's data filtering only. It's compression, yes, but in data space, okay. And basically taking your favorite AI and just applying it and maybe calling that semantic, okay. But this is system 1, okay. Now system 2, which is the harder one and requires slow thinking, multidisciplinarity, and so on, is this one. So here we can look at it through the tasks. So here the task, as I told you before, we need the planning, we need the reasoning, right? For that, you need the compositional. You need to learn concepts and put them together, compose them together, and plan with them, right? You can also look at it through the lens of what kind of desiderata. So, of course, invariance, disentanglement, and so on and so forth. But what can I do with this? Well, now I can actually work on serious use cases that 6G promised to tackle. One of them is this. You have a collaborative robots. What's the syntax they will use? What's the signaling they will use or protocol? This is an open problem today because we will not use 3GPP language. There's no need for it. How do you emerge that signaling entirely from their multimodal sensory data? It's a fantastic topic, right? Because you see, it connects robotics, AI, communication, everything, hardware, right? Another one here, which actually Nokia Bell Labs jumped in, that's why I called it System 1, and I crossed it. They have this base station here in a 3GPP language teaching the signaling to Mac UE learners entirely from data. Kind of an expert teaching students or teacher-student architecture. I'll show you how we kind of went beyond this idea. And of course, all the rest. So this was before LLMs. So now with LLMs, things make a lot of sense. So you have a teacher, prompting a receiver. The receiver maybe have to infer the intent of the teacher and solve a task, things that we have been talking for many years, but now I think they fall very well within this framework. And as I told you before, what we need is really this theory of abstraction. Today is an open problem in many areas. Theory of algebraic compositionality. I think I've said it already many times. And another buzzword, which is interoperability. One convincing way to tackle interoperability is precisely through this framework. You have different models, different syntax. How do you make them communicate? Different robots with different specifications. How can they communicate, right? So I mean, this is basically just a vision. Obviously, we haven't solved all these problems. I'm just telling you a little bit what maybe should be the main focus of many research groups in the world, right? Having said that, now let me walk you through some works we have done in this area. Some of them are naive. That's why you see this baby step here. But I think it's very good to learn from mistakes. So this is the first series transaction paper on this, where we ask the question, how and under what conditions cooperative communication emerges between two agents, a speaker and a listener, and is robust to deviations or different priors or beliefs of these agents. Okay? And you could solve this in many ways, but for us at that time, we were really looking at different areas which look at linguistics, okay? Because this is, of course, inspired from how humans communicate, right? And it turns out we found very interesting framework from psycholinguistics. There's something called the triangle of meaning, which is here. So if this is your sensory data, maybe depending if it's vision, text, haptic, tactile, then what you do, you have to map this to some sort of thought or concept. So we really like this idea because that's exactly what we want. We don't want to send the sensory data. We want to send the concept, right? And then once you have the concept in your head, you symbolize it. That's the other one, okay? So that's a triangle of meaning. And therefore now what I have a speaker listener. Speaker has some modalities, sensory data. And then the goal of this whole exercise was really to use a two triangle, if you want. So this guy has a triangle, this guy has a triangle. And now what will happen is that the speaker has to basically communicate the minimum amount of concepts to the receiver, such that the receiver understands and infers the intent of the sender, okay? Entirely from data. That's really, really what we did. A very basic idea, actually. And then, of course, here, I mean, the goal really is one, to infer correctly the intent from the sender, right? And then, of course, the speaker has to do the hard job in terms of sending only the most important information, okay? And of course, we shouldn't be naive here. I mean, this whole topic of semantic comm also is nothing but, of course, this is a high-level description of a trade-off between communication and computing. In other words, here, the thinking, the planning mean how many local iterations the speaker has to think about the receiver to send the information. So I think I'll show you some results on this, okay? Good. Now, of course, how do you model all this thing mathematically? So I actually found a very neat information theoretic formulation, which is very basic. So you cannot do more basic than this. So you have this speaker and listener, which are going to basically minimize this loss function with respect to their own. This is basically referring to the speaker's context. This is the listener's context, and M is the mutual context. So the goal here is really that these two, speaker and listener, converge to the same mutual context or space, right? If they do that, it means they have communicated. And I'll show you what I mean by that. So mathematically, this is the loss function. This is the joint entropy between the context of the speaker and the mutual context. This is the entropy of P, right? This is alpha. So this is the first part, this is the speaker, and this is the listener. The whole point here really is going to be about an abstraction. The speaker has to abstract, right? He has to compress all the data in terms of one or two concepts, right? And then send that to the receiver. But he has to be careful because if he compresses too much, the listener cannot understand. So you see there's a game here, there's a dance between the speaker and listener such that you have to do kind of rate distortion, but in concept space. If I compress too much, it's great for me because I can store better, but I cannot communicate. On the other hand, if I just send you everything, that's kind of not good in terms of bandwidth, right? So actually we formulated this again, as I told you here, and then you can show mathematically that this iteration, this mutual iteration between the speaker and listener, right, can be written here. I don't want to really go into the detail, but it can be proven that actually it converges towards this common mutual context, okay? Yeah, so alpha and beta, I told you, so alpha and beta really have to be traded off because again, too large, not good, too small, not good, right? And really what we are doing really here is just a rate distortion, not in data space, but in concept space. Okay? That's essentially what we did. Some special cases, which was also interesting here, if you take, for example, a log loss constraint and uniform prior, right? You end up with a famous mathematical framework called entropy regularized optimal transport, and you can solve it in linear convergence times, which is of course interesting from a theory perspective. But yeah, if it's not log loss, you lose this property, and you cannot really invoke this theory, right? But really, in short, here, just take away is this in communication here is really just an alignment, a transport from the belief of the speaker to the belief of the listener. They have to kind of iterate, convert to the same concept. So let's take a look at some results. So here what we show, this is the reliability, the fact that you can successfully infer the intent, alpha, beta, and these are the self-iteration times, t equal 20, 100, 200. So you see how many local iterations the speaker has to run its algorithm somehow to send the most informative concept to the receiver. So very interesting here because you can see, in fact, that it has to be very slow. So it's slow thinking, right? So you see here, you have to wait until maybe 200 iterations before you reach the highest reliability here for some, alpha and beta, right? So we are here, okay? So faster convergence is not good. Okay? We have to let the algorithm somehow, explore all this common space, if you wish, right, before communication can be actually achieved, right? We also looked at the trade-off between, again, reliability. This is communication round. So would you rather communicate many times, or would you rather compute locally first and communicate? That's a bit what we did. It's kind of straightforward, right? So you can see, for example, at 200, again, self-iterations, maybe you need less communication round, right? Versus if you don't, you see you're here, few iterations, if you wish, maybe you have to pay cost in higher communication. Okay? Things which are very, right, I think, intuitive. We also looked at the kind of payload size here. So this is the semantic representation length versus iteration steps. System 1, where you send all the concepts, right? System 2, where you find really the minimum amount of concept that you would share with the receiver. So you can see the gains here are huge, but of course, these are really, really expected, okay? Good. So some self-criticism here, in fact, okay, there are some caveats because one, in case you haven't noticed this, there's no machine learning here, okay? So somebody could take this and just apply AI there, which is, I think, very interesting if it's done the right way, meaning that we assumed here that the mapping between data and concept was known, okay? It's kind of a bipartite matching graph, but of course, this is not true all the time. And it's point to point. But more interestingly here, there is no structure. I pitched structure since the beginning. There is no structure here. So what are you talking about, right? And of course, no algebraic compositional. So therefore, we jumped on this idea now of exploring fascinating area of mathematics called topological data analysis, which I would add to the, to the cart of teaching in our universities. So here the idea will be really to look at semantic comm from a simplicial complex perspective, right? So what do I mean by that? So in fact, what we will assume is that data lives in this higher order space, topological space, so k-order simplicial complex, which is something we also use, but we use at the low dimensional space. For example, if you take k equals 0, that's a vertex. K equals 1, it's an edge. So typically we stop here. This is a mutual information between two random variables. But hey, that's, I mean, why do we have to stop here? Here you look at triplets. Here you look at tetrahedron. And what's very nice about this structure is actually both topological, right? I mean, you can see the shapes, but also algebraic. You can then maybe take this, this triangle and add another triangle. You can piece out, compose different shapes. And I think it's great. Now, you can write this in a fancy mathematical way, but I really don't want to bore you with here. This is just a way to write this from a categoric, theoretic way. And why would you do that? It's just to say that there is this universe which is composed of shapes, right? And how do you go from one shape to the other? That's the whole point of this area. And that's nice because it gives you the syntax, okay? So this is basically just syntax, huh? I go from here to here, that's an arrow. I go from here to here, that's another arrow. And I go from here to, but I haven't done anything because I'm after semantic information. So I need to go to another space where I have to calculate some, let's say, quantities and use those quantities to measure information, okay? But now the question is, how do I do now message passing on these kind of structures? How do I do a convolution? And it turns out there's a lot of existing theory. For example, there's this idea of Hodge theory, which is basically the extension of graph Laplacian, is the extension of graph neural networks. So basically doing signal processing on higher order topological space, okay? So now what we do here, what we will be basically doing is to track this. You can see here, we will track this space when I go from, so let's say, if I put data on my vertex, this could be a feature. It could be a feature of your image, right? Or your signal, right? How does that feature change when I go from this lower dimension to a higher dimension? That's exactly what you see here. You see 0, right? You have this strange looking word. I mean, this is just the co-boundary operator in this framework. And then you see you go from k equal 1 to k equal 2. So I'm trying to track how information changes or not when I go from low dimension to high dimension. And that's exactly what you see here. That's my operator here. And this operator is great because, in fact, it extends Laplacians. So everybody uses Laplacians for sure, but now this I'm looking here really for the kth order Laplacian here, right, which is given here by this equation. So this is the adjoint, right? So in case you didn't know, this is the co-boundary operator at order k. It's adjoint multiplied by the same thing, right? Plus the same from the lower dimension. And just with this quantity, I'll show you how much gains we can get. Because in case you have noticed here, I'm really trying to hunt for a structure and track information dynamics over this space, okay? Now also, how do you do convolution? Well, here's very easy. So if I give you a complex, a kth order complex, and I have the Laplacian, right? I told you at order p, and then I can just train these weights here, basically to train do my convolution layer, as opposed to doing it, let's say, in CNN, convolutional neural network. Okay, this is just the Laplacian. Just how do you go from zeroth order to 1th order? So here, what we are doing, by the way, we are moving information between triangle to triangle. See, when you work with lower dimension, you're just moving information from a vertex to another. Okay, but we know that information lives in high dimensional space. That's the point. Okay. Now, having said all of this, now what we do with this structure? Now, what I will do, I have a sender, I have a receiver. So now you can tackle this in many ways. I'll just show you what we did. Here, what we will basically be doing is encoding. So again, what is the order that the sender has to choose to basically encode the simplices where the information lives, and then send that over wireless to the receiver. And then the receiver, given the order, because he has to look, should I go to k equal 1, k equal 2? Then he goes to that dimension and decode the missing information. So it's kind of filling in the blanks, okay, of the missing information, which you can do for free because you can infer that information from lower order information that you already have, but also what the sender sends you, right? So you can write this is a loss function, basically trying to decode two things. The structure, this is very important. I'm trying to decode the structure, meaning the kth order simplicial complex. And once I do that, I decode the function on top of it. That's really structure, decoding, and function. Exactly what the brain actually does, okay? So these are just some results here, very straightforward. So this is the topological error of different embedding orders when I remove 50% of the data. In fact, just to show you how powerful these ideas are, of course, in this toy example, perhaps, right? So this is the error. This is communication rounds. And here I'm showing you a lot of plots, but basically just a trade-off between order and SNR. So if I am at a very low SNR, where things are very bad, this is a harsh environment, or even missing data, right? I have to go to higher order, because now when I go to higher order, I can actually retrieve that information, even if it's noisy, even if I don't have it. That's essentially what you see here, right? That's for topology or geometry. And then, of course, you just decode the data on top of that, right? On top of that topology. That's the same trend again here. You can see that there is an interplay between the order and SNR. So in short, what I'm trying to show you here really is that the impact of semantic communication, information compression is great in terrible regimes. So low SNR is one, and when data is high dimension, because obviously if there is no structure, let's not talk about semantic. But we know the real world is full of structure. So the idea is we have to learn that structure, use it to compress, to communicate better, to be resilient. That's the idea. And also here, what was nice, in fact, this is maybe a marketing pitch here, but even if there are syntactic errors, meaning the data is missing, no problem. You can recover it at the receiver, okay? So the more structured, the better. Good. Now let me move beyond the point-to-point, because some people don't like it, and they may be right. I mean, what is a toy example? What do I do with a point-to-point, right? So now let's move on to the network-wide or system-level type of ideas, where now I need to learn communication protocols, right? So we will be looking at few works we have done, mistakes we have done, mistakes others have done to help us, plan better. So the first work, in fact, is really this one. inspired by the Nokia work, by the way. So how do you learn a MAC protocol? So now I am at layer 2. Because some people, by the way, believe that the benefits of AI are not in layer 1, are in layer 2 and above. I don't know. For me, I mean, professor, you have to look at all the layers and see what happens. But anyways, this is a discussion with Akyildiz. Here, basically, let's see what we have done. So before that, let's see what Nokia has done. So Nokia came up with the System 1 MAG. I mean, they didn't call it System 1, but I gave it the System 1. Basically, what they have done, they took this 3GPP protocol, base station talking to users, right? So here, of course, an EMBB. So the signaling is kind of simple. Scheduling request, scheduling grant, acknowledgement. And said, can we show that it works entirely from data? Black box. So they model this as a cooperative reinforcement learning problem, and they applied existing techniques. So there is this RILE, reinforced inter-agent learning. Basically, just taking two agents and sticking a communication module between them, and then you do message passing between these two agents, basically, right? And then that's what they basically did, right? And the problem now, my focus was really, guys, there's a problem, because is there any structure? No. They just do garbage in, garbage out, or let's say a brute force, right? And I think we have to stop thinking like this. We need to ask the right question. Is there any structure? Do I know it? Use it. If you don't know it, learn it. Sorry, I mean, right? And now if you look at what kind of technique they have used, they use model-free RL, which is nothing but learning a policy or a mapping from state space to action space. This is very naive. This is a mistake we make all the time, because we just throw in existing tools without understanding. Basically, maybe I should not learn in this state space. Maybe it has no structure. Maybe it's noisy. Maybe I'm learning an action with data I shouldn't use. Okay. So what did we do? Basically, we took their work and we said, do not do this. Do not learn a policy in state space. I crossed it. We have to do it in information space, of course, right? I mean, now, of course, the questions that should be generated in your brain is, what do you mean by information space? Well, here we have a whole catalog of ideas. Do you want to do state abstraction? So maybe I want to compress the cardinality of the state. Maybe some states are equivalent. Are you looking for a special feature? Are you actually doing something smarter? Maybe you're looking for symmetry in your environment, and then using that to compress completely your problem and solve it. That's exactly what we try to do. I think it's a very nice area. This is a heuristic. I have a more theoretically sound work, but let's start with this. So here what we did, we said, I want to do state abstraction. So I will feed in, these are observations, these are the states, channel state, buffer state, okay? And then what I will do, I try to compress this information using a machine learning architecture of your choosing. Here we use VAE, by the way, very simple. And I'm gonna learn this latent representation. Why? Because I'm trying to use it to now compress, number one, to generate different signalings. You can see here the decoder, right? Signaling 1, signaling 2, signaling 3, and maybe I can now think of averaging the signaling, or I can choose the best one, right? Or I can do some mixture of experts. That's exactly what we did. And of course, don't forget, this is a setting where the expert is the base station. So we have access to the, if you want, the ground truth, right? So in fact, what this compression problem is really just given by this quantity here. This is a distance between the policy of the expert, the policy of the UE, or the agent, and then you can write it down and solve it. It's really basic. Maybe the results are more interesting. So this is the total number of packets received, is number of UE. Nokia baseline is here. It doesn't work. I mean, it doesn't work. It makes sense because there's no abstraction. You just use data and train and so on and so forth, right? Ours is here. Of course, it should work. Why? Because I'm abstracting. What do I mean by that? I'm really compressing my state space to learn faster and more robust way. That's really here a takeaway, right? You can also look at it here at the total number of packets versus number of incoming, right? Packets to send, basically. The same result applies. So the Nokia, I think, is somewhere without. So it's here. But here it starts to basically drop, meaning that it cannot generalize. Of course, generalization is all about abstraction. You need to learn quantities that do not change, that are invariant when you change the number of, environment, maybe change users' positions, right? That's what you need to leverage to train models, not just fit in states and action pairs and train, okay? Good. Also now we also realize, obviously, that we need probably one day to jump into symbolic type of protocol, maybe call them neurosymbolic. This is an old word, right? It's not ours. Of course, everybody knows it's GoFi, good old-fashioned AI was the first one, rule-based, and then we dropped it, and then we do deep learning, and then we realized in 2024, okay, maybe that's not a good idea. We need to do both. Of course, we need to do both, right? But for us here, really, we wanted to look at, kind of explore this problem here, this recent JSAC, is can we translate neural protocols, statistical models, into something which is more useful, so symbolic protocol. And why would you do that? For many reasons. You can actually compress, right? You can now test. You can maybe, as I was saying before, maybe try different users and do logical inference. The goal here really is to do logic, meaning ask a question, what if I had 3 more users? What would be the performance? Instead of training data, that model again and waiting for the results. We want to do it in a system 2 way, okay? And then, of course, you can think of maybe you have a partial causal graph, the other base station has another partial graph. How do you communicate, right? That's a bit what we did, really. But let me show you here what we actually did. This is a toy example, really. Even though it's a JSAC, it's really toy example. This is a 2 users. So we took this neural protocol model for 2 users. You see here, user 1, user 2, this is the base station. And we unfolded it. We wanted to look into it somehow, just to use it as a simulator to try every possible activation value, every possible state value, right? And try to compress this, right? So that's what you see here. We unroll it, right? And then what we will start to do is to compress. But how do you compress? This is not JPEG compression. We need to use the right word. So we use this idea of learning equivalence classes of state, action, reward. So now what I want to try to do is, when I take these trajectories, I want to see whether they're equivalent. If they're equivalent in terms of reward, I put them in the same cluster. So we can call it a clustering 2.0 if you wish, right? And this is great because it compresses the whole graph here, as you can see, right? Or prune it if you want, right? But then, of course, you end up with another problem, which is called polysemy. In French, polysemy means one word means different things. But that's okay, because actually we can deal with it now with Shannon information, meaning statistics. We can say this one is more likely to happen. I mean, this signaling, let's say, is more likely to happen than another signal. Okay? But also, of course, here, because I don't have time to go into this, so then what you can do, you can write this in problog. This is kind of logical way of writing this proposition. So this is the uplink clause, the downlink clause, and then the action. Okay? And why would you do that? Is just to run logical inference. What if this happened? What if that happened? What if I drop more users? What's the result? Okay. And just to show you some result, this is the TSNE of the embeddings. This is the neural protocol model. When you compress the whole thing, you can really compress the space, obviously, right? This is for uplink. This is for downlink. Also very interesting now in terms of model storage, memory, and inference. Here we are comparing. You see here the first, this is NPM, neural protocol model. The model storage 4 million to store all the weights. Here we don't do that. We compress, as I told you. We throw away all this users' information. Now you can see 1,000 parameters, more than enough. So huge gains, right? Inference, this will be 14,000 flops to run inference time. Here, no, it's completely, it's orders of magnitude better. Why? Again, because we're compressing this monster, this NPM, to something compact that you can use to compress, to do maybe logical reasoning, okay? Good. And of course, maybe this is just, this is basically the use of semantic entropy. So now this is an entropy, not over random variables, but entropy over different signalings. Okay? And then you choose the best one, the more likely one. So if you have, let's say, to deal with this compression polysemy problem here, one way is really just to choose the best protocol according to the semantic entropy. Okay? Good. Now let's switch gear a bit, something a bit more interesting for theory, let's say. Now we look at another type of problem. I want to explore the geometry of the data as a topological state abstractor to learn robust protocols. So there is this very nice idea here. And of course, here we focus on a cooperative navigation use case as an example, obviously, right? So somebody will also take this example Don't think too much. Throw in machine learning, right? So this is basically this is a field of view of the navigating agent. This is the other field of view. You know, garbage in, garbage out, right? And then of course, how do you do that? So of course, Nokia maybe or other company or myself even, we just again take this cooperative partial observable MDP. And then of course you have action here is to move, because now the action is not only to communicate, but to move in the world. How the agent should move to explore the map. Okay, we don't want to do a redundant exploration, right, of the map. We want a protocol that allows the agent to quickly discover the map. Same thing again, no structure, no abstraction, no planning. And I think now you know it. This is the reason. Now what we did, we said, don't do that. Learn in information space. But now we had to kind of roll up our sleeves now, because now we want to do things properly. So now what we'll be using this notion of symmetry, deformation, which are coming from topological data analysis. So now, if you remember my speaker listener example, now what I will do, I don't want to work in this field of view. No. I want to work in the semantic space or information space, which is gonna be how it's kind of a fingerprint, or how the field of view of the agent is encoded in some sort of strange space, and I'll show you what I mean by that, which will allow them to communicate much better, and it's robust. So we use this notion of persistent homology. If you're familiar with that, if you're not, no problem, I'll show you how. And what I like about this is it gives me a very good grounding of what level B means, this meaning. What's meaning? Well, meaning here will be really about equivalence classes of data, kind of an abstraction. I'm going to take many fields of view, and I'm going to take the symmetry, I'm going to take deformation, right? And then I'm going to put them in the same class. That's meaning for me here, right? That's actually what we will do. So think of it as a compressed, if you want, POMDP or something. But this is not compression, again, in a JPEG sense. It's compression really in the abstract space, okay? Very good. So how did we do that? So first step, right? And this is basically depicting these fields of view. So if you see, this is what the agent sees. So you can see there's a lot of symmetry here, right? So what we will do, we will compress, we will exploit the symmetry. There is something called quotient MDP, right? With respect to rotation. You can see here, if you rotate these guys, it's the same thing. So why would I need to learn a policy from state space or action space without exploiting this? So you have to do that. So here, this is what you see here. Definition of a quotient MDP. I mean, I don't know how much time I have, but this is basically saying that if you have any group, meaning translation, rotation, acting on the state, it should give you the same reward. That's really what you see here. And also the transition, the state to another, right? You should maintain this property. But that's it, in fact. So you have group acting on an action, right? And group acting on the state. And you want to find this equivalence in terms of states, equivalence in terms of state actions, okay? Then once you do that, then you want to see, is there any other structure I can exploit? Maybe if I deform the field of view, right? If I take your eyes and maybe deform them, you can tell me still this is a cat or a dog, right? How would you do that? Again, we have to compress this MDP, you see, from here to here. And the question is, how do you do that, Mehdi, right? So here we explore this very fascinating area, which we call, so there's something called equivalence up to deformation. Okay, so here it was equivalence in terms of symmetry, right? Now, how do I construct this equivalent classes or clusters here, because it is a cluster one, right? And what do I mean by that? So here we went to this, again, area of homology, cohomology, which is actually very interesting because it gives us a new notion of information. It turns out, in fact, this was not known to me, this French mathematician René Thom, very famous actually, it's a field medal, said something very powerful. So he said, when you use the word information, because information means everything, right? It's a polysemous word. He said, use the word form or shape. And to me, I think it's very powerful because now what I will do, I will take my data, which could be point cloud data, whatever, right? Time series data, and I'm gonna try to learn topological invariance of the data, right? And then that gives me now this space where things are equivalent. It will give me some barcodes. So, I mean, this is a very known technique in topological data analysis. So you take this point cloud you see here, then you have this radius. So for example, for 0.6, you draw this edge, right? So the edges are born. At 0.8, the triangles are born. At 1.2, the tetrahedrons are born. So you see, I'm tracking again the same way as I showed before, this invariance when they are born and then when they're dead. So I want this persistence of this invariant as a measure of robust information. So that's encoded also here as a barcode. You can see here quickly, right? So 0.6, then the 0.8, you see? So I'm gonna use exactly this as my information space, okay? That's actually what you see here without going into much details. Visually is this field of view. This is the corresponding barcode or death and birth. So you see, you have some, you want to be born early and die late, kind of longevity, right? So you see, this guy is dead here. These guys are dead too early. This is noise, topological noise. So I want to be born early and die late, okay? But also these guys, you see, syntactically look different, but semantically the same. How? Well, because when I look at their difference between their barcode or their persistent diagram is the same, okay? So I hope I conveyed the message here. But in short, that's what we did. We have nice results here. I mean, just to show you quickly, this is the reward comparing with some baseline, basically variation autoencoder and so on and so forth. So we have gains here. This is very good. This is the representation of a VAE, which doesn't exploit structure. And here is a much cleaner representation of this persistent diagram, because again, I'm encoding all the structure, right? And then some proofs here. I don't have time, obviously, to go through this, but just to show you that things are proven, meaning that once you compress all this cooperative partial observable MDP to solve an approximate version of it, you can still maintain some balance with respect to the errors you may have. Okay, very good. Now, what's next? I'm not keeping track of the time. I hope it's fine. So what's next, really? So in fact, we are not there yet, because this is still system one. What we have done so far, we didn't use model free, meaning state action policy learning. We did some sort of filtering. We used state abstraction. We said these states are the same, okay, compress, right? Via topological data analysis or persistent diagram. But what we are missing, really, the takeaway today also, is really we are not planning. So the right way to do it, if you look at the brain at a very high bird's eye view, you have the perception module, the actor module, the memory module, which are system one at best. What we are missing is this thing here, the world model. And the world model right now is trending a lot in AI. Some folks in communication, of course, are grabbing that concept. We are trying to study a little bit more what do I mean by world model, right? But here really you want to learn a multi-model world model. Why would you do that? One is to plan. You want to anticipate what will happen. So you need to do this anticipation, not in pixel space, in latent space, right? And you want to anticipate, adapt, so on and so forth. That's, again, what human brains do all the time, okay? So how do you do that? How do you learn world models? Well, this is actually the Yann Lequin. I hope you know Yann Lequin is the head of Meta AI, and he wrote this vision 2 years ago, which he says, this is it. This is the path we should follow. Forget about the previous AI directions. And I show you, and maybe you can discuss it later. He tells us that now, guys, abandon generative AI. Do not do that. But wait a second. Don't do that for what? Not for reconstruction or generating high pleasing videos. No. For planning. Because to plan, you should not reconstruct. That's the idea, right? So he tells you what he wants to do is to learn a semantic representation from data. This is an image, for example, but it could be whatever you want. You push this to X and Y are pairs of images. One is cropped, maybe one is rotated, and so on. And then what you want to do, you want to predict the semantic representation of X from the semantic representation of Y, or vice versa. If you can do that, then you can use the semantic representation to plan. So that's his paper. He tells you now, I mean, everybody should read his paper, by the way. The path forward in autonomous AI is this: representation learning, perception, and planning. So the big deal is really here. To plan, I need an internal simulator in my head that models base stations, robots, interactions, views. This is a very strong message, of course, he's sending us here, which maybe is nothing new, but it's good for us, right? To somehow see where this is heading. So he did this, he called it JEPA, by the way, Joint Embedding Predictive Architecture for text, for image, and for video. But I think this is heading towards multi-modal, cross-modal multi-scale JPA, because of course we shouldn't forget the brain doesn't have one representation. It has a nested hierarchical representation which you can then use according to the task, right? I mean, there's no point, you don't have time to run these computations if you're driving. I mean, you have a latency, right, budget there. But the point, we have to learn hierarchical representation, which I can optimize over according to my budget. But for us, what we did, we applied it in a recent work, by the way, under submission, in a remote control problem. So you may have a video here, and maybe you have a remote controller, right? So you baseline would be send the video to the controller, don't do that. Compress it, don't do that. So we trained this latent representation that we would send to the receiver, right? So first you have to do that, which is not obvious, right? Because you have to learn the invariant representation across video frames. And that's what you send to the base station. And then the base station gets this, and then you start to plan, to predict basically how the remote sensor, if you want, will behave, and then send it, actuate it over wireless. That's really what we did. So it's an old problem, but we use this kind of idea of warm model such that the controller plans ahead in case something bad happens, and then actuate the receiver. Okay? So you can see the gains are big because, in fact, yes, I mean, when you compare it to sending raw state, bad. When you compare it to compression, is bad. So you can see here, even though you lose 5 packets, no problem, because the controller has a model of the world, model of the object, right? So you can really, you know, use that to plan, in fact, and actuate. That's actually what we did. Maybe fast forward a bit now here. I told you these LLMs, which are a bit annoying in the sense that it's not forcing us to think, but you can be sure that there are people now thinking about system 1 versus system 2. So we worked on system 1. You can reproduce the result. Actually, no, because you need to invest in GPUs. Some locations do not have that. Even from that perspective, it's not the right track for university. But what we need to be doing, of course, what's missing in LLMs today, and people already talking about it, is exactly this warm models. They don't have warm models. They cannot think. They just spit out based on trained data. That's the whole LLM state of the art today. Of course, this is moving. This is changing over time. But the point being, yes, warm model is missing. Okay? And of course, we have to go towards smaller model, of course, multimodal model, of course, and planning. So you can see it's a very nice sandbox environment that connects basically many, many disciplines, right? And maybe coming perhaps to the end, or maybe my last 2 slides here. So also a very nice area of semantic or multimodal sensing semantically, because sensing is an old topic. Fusion semantically, because fusion is an old topic. And planning and communication. This is fascinating because, in fact, I can find myself, because let's say you have a RF signals, image, LiDAR camera. They may have totally different syntax. Maybe RF is written in vector space. Maybe images are written in some other syntax. How do you fuse their information? This is number one. This is within one brain. But how do you do it across brains, right? I think this is really, really, really interesting. And of course, yeah, now let me, one word really about resiliency, because this is work in progress. But in fact, resiliency and semanticum are actually extremely related. The word resiliency, by the way, just to show you here, this is taken, by the way, from internet. These are stressors, right? Stressors, bad stuff happens. Okay, so robustness is here. Resiliency is here, meaning you can still maintain and sustain your operation better over a longer time scale. Or maybe when you go down, you bounce back very fast, right? So for us, we have been thinking very carefully about these things, and we can find ourselves again there. So resiliency can be seen through 2 different ways. So as elasticity, like spring, right? So, you know, a spring here goes beyond its favorite state, then it goes back. Reactive, nothing new. But there's no paper on this, okay? And also there's no planning here. Now you know why. There's another way of thinking about resiliency as plasticity. Exactly as the brain does. The brain, I told you, plans. How? Using a warm model. Because if something bad happens, I update my structure. I rewire my internal representation to solve the task, okay? So this, I think, fascinating here, because it kind of basically give us maybe some good grounding for speaking about resiliency. So resiliency and semanticon are exactly the same thing. The only difference is the resiliency is negative in the sense that things always will happen, wrong things will happen. So enforcing conditions will always happen. So how do you deal with that, right? So you have to continually sense, adapt your world model, because your world model may be expired, may be wrong, may be tapped into, right? And always ask the question, if something bad happens, what will be the best response? That's how you should justify to versus reliability and versus robustness. Okay, just some.
Mehdi, I'm really sorry to interrupt you because
Yes,
we are
I'm
15
done.
minutes above the time. I know
Okay,
that you are very.
actually, I'm done. This is my last slide. So.
Yeah, you love the topic and you are in the subject. So I'm really sorry because we are 15 minutes above the time.
Okay.
And so
basically,
very nice, really. I enjoyed it. There are many incredible new ideas here. So
maybe we can stop here really and take.
Yeah, I will suggest it, and also I hope that we can try to get some questions from the audience. It looks like there is no question, but I can ask you a question. And
how can I see you first of all? I'm just trying to. Should I stop sharing or yeah?
Yeah, it's okay. So we can leave it. So so you mentioned about these large language models. One of the problems is that when these large language models are somewhere in the cloud, and when you try to access them, especially for the real-time cases, the end-to-end latency will be so high that the real-time communication will be extremely affected. And you also mentioned that small language models, that would be really a way to go, like tailoring them into certain applications. And then accordingly, you create subsets of these large language models. And then the question is, of course, where will you deploy them, right? Maybe in the edges. So what is your opinion on that? So because you mentioned, that's why I'm repeating.
No, I mean, that's a very important topic. And of course, it's like fast thinking versus slow thinking. So the right way to look at it now, one way to deploy them, I think we have to talk about these pre-trained models. So you have to, because there's training and inference. I think the way now I see it is the following. We will have a library of pre-trained LLMs on certain data set, right? And then what you would do, and of course you can optimize for maybe to be run on a given hardware, or maybe with some resource constraint budget, but that's not enough. Then what you would do, because they are trained independently, right? Now what you will face the problem, and once you put these agents together, these multi-agent LLMs, which is actually the right word to use here, is how do you now emerge communication or signaling or protocol or structure between these agents, because they have a different understanding of the world. You see what I mean? And I think that's actually what Microsoft is doing now here, right? So you pre-train, you put them together, and you try to kind of make them communicate. And I think it's really interesting because there's no sense to do it from scratch and interact with the environment and do random stuff. So that's one way, yeah. And of course, a small part, why, right? I think just to compress, right? So
I have one more question. Actually, two more, and then maybe some people will show up and ask questions. There is one, but let me ask you, and then maybe more will come. So now the question is, there are many papers existing, as you know, and somehow I miss, maybe I didn't see it. What is a metric for quality communication in terms of semantic communication?
You said qualitative, right?
Metric, yeah.
Just repeat, because I heard qualitative communication, right?
In terms of semantic, yeah, so like what is the metric that we should use, kind of like optimization of that metric for quality, in other words, quality metric in semantic communication. Or I know. And then also equally, how do we determine the quality of data? Because the quality of data may be different for each person and each machine, right?
Yes, absolutely.
So do you have any
very
thoughts about those?
Yes, I can give you my insight. Yeah, because I mean this is very important. So first of all, I think it depends on the use case. First, you have to set up the use case. Let's say if it's a collaborative robotic scenario in a factory, you will have to deal with how do you know that the task is achieved, right? So you need a metric. So for sure, I mean, what you should have multiple metrics first of all, right? So first the achievement of the task, but you want to have intermediate also, right? Kind of metrics. So for example, their model operates as it should be. They are not, you know, drifting away or maybe spitting nonsense, right? This could be one, right? But the easier point of the question is the smartness of the data. That's part of the agent. So agency means that you have to actively sense, right, and sample the most informative information for you. You cannot just collect every type of big data type. No, this is very important, right? So it's kind of the active sensing inference paradigm, right? Yeah.
So there is another question by Hongji Guo. In topological data analysis, including the persistent homology, it is challenging to handle noises in the data. The noise may introduce new birth-death pairs.
Right.
Did you use any persistent homology features besides the persistence diagram to reduce the impact of data noise? It's a very good question.
Yeah, very good question.
Actually, he's one of my grandchildren, so I work with him. So it's a very good question.
That's why. Yeah, so I mean that question is native to topological data analysis. So for us, of course, we can't deal with that because, of course, you optimize first of all the radius, right, of those point clouds I showed you, right? So you can show actually where the topological noise is. This is not a problem. Now, of course, if you deploy this in practice, yeah, maybe it's a different story. But we haven't seen in our result any problem with that. I mean, that's the simple answer, in fact, right? But but you have to deal with topological noise. This is no doubt about it. Let me see.
So
that was the question, by the way, huh?
Yeah, I hope so. Mohsen Iftirak wants to ask you in real time, but I think we don't do that, so he should type it.
No, actually, the system doesn't allow participants to intervene.
Type it, right?
Yeah, either type or we can converge now to wrapping up this session. And Alessia will take over. And I thank you again for this outstanding, exciting talk. Again, you lost yourself, Mehdi, and you were like in your element. I always enjoy your talks. Like you really forget yourself, like you're in a trance, you know.
That shows, I don't see myself, which is annoying.
No, that shows how deep researcher you are. Really, you're enjoying the work you do. So I really appreciate it as a person, but also as a friend. But thank you again, and Alessia will take over and ask you some questions.
Thanks a lot.
And I'll be back again. Okay.
For sure.
Thank you so much, Ian. Thank you, Professor Bennis, for this very interesting presentation that you gave. So let's move to the Wisdom Corner, live lessons, which is based upon the idea to give a personal touch, actually, to the series of webinars. So I would start, if you agree, with my first question. So I would like to ask you, which is your hard-earned life lessons or failure that you would like to share with us that might help somebody attending the webinar today?
Sure. I think the discussion on resiliency was very related because, in fact, resiliency teaches you to always, learn from mistakes. I think it's very important at the early career, but also even a later one like mine, is to really learn from mistakes. So this is a skill that maybe some of our students do not have or should have really, because it teaches you a bit how to adapt to different situations, how to solve new problems you have never encountered. So for me, this is very important. Number one. Number two is this multidisciplinarity. As you can see, I have been fond of this since I started doing research. And before multidisciplinary, the word maybe was hyped up a bit like nowadays, but really we need students that also are thinking in a multidisciplinary way as opposed to in a siloed way.
Okay, thanks. In which fields and which topics would you recommend students to study today? Is there any current trends or emerging areas of research that you find particularly exciting or promising?
Yeah, as of today, I would say, so all this topological data analysis, very important because it teaches you things about geometry, right? The geometry of the data, right? I think it's very fundamental. But also you have, of course, I mentioned logic. Logic is a tough one, but I think it's worth at least to learn some of the fundamentals there, obviously, right? Which means going beyond probability theory, because all what we have been taught, unfortunately, maybe, also, is only statistics. So what goes after statistics is, there's topology, geometry, logic, right? Yeah, I recommend this.
Thanks. And what advice would you give to young people interested in pursuing a career in academia or research? Which key skills you believe and qualities are essential for success in this domain?
That's an important question, yeah. So I think for me, nowadays, I really look for curiosity-driven researchers. I think this is exactly what we don't have or are limited. Yeah, you have a researcher who first has an internal reward why he's doing what he's doing or she's doing. I think this is as opposed to being fed a task and you do this and you come back to me. So this curiosity is really fundamental, and it's related to basically, I think, finding connection with other areas, because sometimes we forget that this problem has been solved in a different area. So how do I bring that knowledge from that area to my area? This is science, by the way, right? This is really the principle of science. Don't be isolated, because maybe the solution is somewhere else, right?
Yeah, definitely. Intersectoral disciplines,
Absolutely.
definitely very important. What initially sparked your interest in your field of study, and how did you pursue it?
You mean my research?
Your own study, yeah, your own study at the beginning of your career.
Right. So in my case, I did my PhD in, let's say, I use game theory to model the strategic interaction between telecom operators or base stations. How do you share limited resources? And you model it as a game. So at that time, there was this nice movie called Beautiful Mind, which is really an inspiration for me. Yeah, so finding Nash equilibrium and so on and so forth. That was one. So that was already my multidisciplinary research. And then from that, I took it and I applied it to optimizing, let's say, 4G in terms of many small cell base station, how they again share the network in a totally distributed manner. And machine learning was natural for me because, of course, game theory and machine learning are connected. And I just grew up, let's say, as a researcher exploring different areas. Some areas I refused to even look into, but now I find myself doing that because somehow everything is connected, really. I mean, and also maybe if I can mention, I find inspiration a lot from novels. So, for example, I worked a lot in ultra reliable, low latency communication. At that time, it was again a word which is just used. Maybe there were heuristics, but I missed the math. So I read this nice book called Black Swan by Nassim Taleb. Very nice book. And actually, it's all about extreme events that happen with low probability, but if they happen, it's terrible, right? So I used that framework to model your LLC. And I think it's one of my most cited paper today. And now we move 2024, now it's resiliency. I think there's something to do there. Right?
Thank you. Very interesting. My last question. Could you tell us one of the most tangible contributions that you have made in your career that had a direct impact on your life, or professional or even personal, and on others' life that you are most proud of?
That's a tough one. Contribution-wise, I don't know. I mean, people can say about that, but I mean, if I can pick, yeah. So the URLLC paper, I think it's really a baby of mine, maybe that I really enjoy reading it even today. But of course, as I told you, I grew up as a researcher, as a human being. So now I start myself looking at neuroscience a bit, and I see how much I don't know. So that's what maybe I was saying that keeps me a bit excited is I'm much more modest than before. And I think that's kind of nice for myself to learn more and more. And contribution-wise, I mean, people can judge, but I think that if I manage to make a nice contribution in semantic communication, I think that would be nice because it somehow can also bridge not only my area, but many other areas, because in fact, communication sometimes is taken for granted, but robotics needs it, LLMs need it, many areas do need communication. So I think maybe that could be mine.
Definitely. Thank you so much for sharing your experiences and your suggestions. So Ian, if you come back with us, we just
Yes,
close
I'm
this
here.
webinar.
Again, thank you, Mehdi. It was enjoyable. And I hope to see you somewhere again in Europe or in Abu Dhabi.
Abu Dhabi.
Yeah. So, Alessia, you want to announce that we have another speaker next
we
week?
have basically a webinar every week this month. So we'll have our next one on the 11th of June. That would be with Professor Albert Zomaya from the University of Sydney, Australia, at 2 o'clock Geneva time. So thank you so much again, Professor
Thank you so much,
Bennis. Thank
Alessia,
you, Ian.
Thank you.
Everyone. Take care.
Thank you.
Bye-bye. Bye-bye, guys.
Bye-bye.
Bye-bye. Ciao, ciao. Bye.
Ciao.